Imagine you're on the fastest spaceship ever built, zipping past stars and nebulae at a speed that defies imagination. The engines hum, the controls glow, and outside your window the universe rushes by in a dazzling display of cosmic beauty. What would the universe look like from your window? Would the stars smear into streaks of light, or would something even stranger unfold before your eyes? As you gaze out, you might expect everything to blur, but the reality is far more bizarre. Over a century ago, Albert Einstein realized the universe has a strict speed limit, the speed of light. Nothing, not even the most advanced spaceship, can break this cosmic barrier. When you approach this ultimate speed, the universe starts to play tricks on your senses. Space and time themselves begin to warp, and the familiar rules you know start to bend. Einstein's theory of relativity completely rewrote the rules of space and time, especially at high speeds. Suddenly, the universe wasn't as simple as it once seemed. One of his most famous predictions is called length contraction. Objects moving close to light speed appear squashed in the direction they're traveling. It's as if the universe itself is squeezing them. But what we see with our eyes isn't always what's actually happening. Our senses can be fooled by the strange effects of relativity. Our eyes capture light, and light takes time to reach us. The faster something moves, the more dramatic this effect becomes. At near light speeds, this delay changes how we perceive moving objects. The world outside your spaceship window would look warped and twisted, not just blurred. The light from the back of a fast-moving object has to travel farther to reach you than light from the front, creating a strange visual illusion that bends reality. This delay means what you see is a complex distortion, not just a simple squashing. Shapes twist, colors shift, and distances become hard to judge. It's a cosmic magic trick, a mind-bending illusion that puzzled scientists for decades. Only by combining Einstein's insights with new discoveries could we finally understand what our eyes would truly see at the edge of light speed. For decades, physics textbooks claimed that speed squashes things, turning fast spheres into flattened disks. This idea, called length contraction, seemed logical from Einstein's equations, but it ignored a crucial detail. We see objects via the light they emit or reflect, not instantaneously. When you look at the sun, you see it as it was 8 minutes ago. Light takes time to travel. At near light speeds, this delay becomes dramatic. Imagine a super-fast cube flying by. Light from its front reaches you first, while light from the back lags behind. You're seeing different parts of the cube at different moments, not a single snapshot. Your brain assembles a picture from old and new light, creating a distorted, time-lapsed image. This realization changed everything. The squashed image isn't what you'd actually see. The real visual effect is far stranger. Two physicists in the 1950s set out to solve this puzzle. Their work would reveal what we truly see at the cosmic speed limit. In 1959, James Turrell and Roger Penrose, two brilliant physicists working independently, finally solved a perplexing mystery that had puzzled scientists for decades. They discovered that when you properly account for the time it takes light to travel from different parts of a fast-moving object to your eyes, something remarkable happens. Instead of appearing squashed or compressed, as many had assumed, a fast-moving object actually appears visually rotated. This surprising phenomenon is now known as the Turrell-Penrose effect. At speeds approaching that of light, what physicists call relativistic speeds, objects don't just shrink or flatten. Instead, they seem to turn or pivot before your eyes, as if revealing a new angle. For example, imagine a sphere racing by at nearly the speed of light. To your eyes it still looks round, but you can now see parts of its surface that would normally be hidden from view. It's as if the object is presenting more of itself to you as it speeds past. This effect is so striking that it almost seems as if the object is showing you its backside, even though it never actually turns around. The explanation lies in the way light from the trailing side of the object has time to reach your eyes, revealing surfaces that would otherwise remain hidden. The finite speed of light creates this visual illusion, blending reality with perception. The Turrell-Penrose effect is a combination of two things: the real physical length contraction predicted by special relativity, and the visual illusion caused by the delay in light reaching your eyes from different parts of the object. These two effects work together in such a way that the expected squashing is cancelled out, and what remains is a rotated appearance, completely changing our expectations of what we'd see at high speeds. For over 50 years, physicists and artists alike Imagine the visual consequences of relativity incorrectly, at least in terms of what the human eye would actually see. The true visual world of relativity is far stranger and more fascinating than anyone had guessed. The universe at high speeds is a place of bizarre rotations and unexpected perspectives, not the cartoonish flattening once depicted in textbooks and popular science. Even the simplest shapes, spheres, cubes, or cylinders, perform a kind of visual dance as they race by, their forms twisting and turning in ways that defy everyday experience. Yet, for decades, no one had actually witnessed this effect with their own eyes or in experiments, until the advent of modern simulations and high-speed imaging made it possible to finally see the Terrell-Penrose effect in action. Let's follow a glowing cube as it speeds past you at nearly the speed of light. Imagine standing in a laboratory, watching as this cube accelerates to an unimaginable velocity, its edges shimmering with energy. At these speeds, the world as you know it begins to change, and your senses are about to be challenged by the strange rules of relativity. At rest, it looks like a simple square, solid, familiar, and unremarkable. Its faces are flat, its edges straight, and nothing seems out of the ordinary. You could reach out and touch it, and it would feel just like any other cube. But as it begins to move toward you, you might expect it to flatten, squashing into a pancake shape. Instead, something far more surprising happens, defying your everyday intuition. Thanks to the Terrell-Penrose effect, your eyes are treated to a visual illusion. You don't just see the front face anymore. The cube's appearance transforms in a way that reveals more than you'd expect. Light from the trailing side, which would normally be hidden, now reaches you. This means you see both the front and the side at the same time, as if the cube is revealing its secrets. The cube appears rotated, as if it's turning to show you around its corner even though it's not actually spinning. This is a direct result of how light travels and how your brain interprets those signals. Straight lines seem to bend and warp, as if the very fabric of space is being twisted by the cube's motion. The familiar rules of geometry no longer apply. When the cube is directly in front of you, something even stranger happens. You see its back face. Light that left the rear of the cube long ago finally catches up and arrives at your eyes, just as the cube passes by. As it moves away, you continue to see its back, almost as if the cube is rotating away from you, giving you a parting glimpse of its hidden side. The entire sequence is a mesmerizing dance of light and motion, a visual symphony orchestrated by the laws of physics at extreme speeds. A rigid, ordinary cube transforms before your eyes into a rotating, curving object, its shape and appearance constantly shifting as it races by. It's not magic, it's the weird, wonderful beauty of relativity, a reminder that the universe is far stranger than it first appears. This is how the universe truly looks when you approach the ultimate speed limit, where time, space, and perception all begin to blur together. And now, thanks to science and imagination, we can finally see this hidden reality for ourselves, and marvel at the wonders that relativity reveals. For over 60 years, the Terrell-Penrose effect was just a theory. No one could film a cube at near light speed. But a team in Vienna had a clever idea. Instead of speeding up objects, they slowed down light. The key is the relationship between an object's speed and the speed of light. By making light move much slower, they could create the same effects with objects moving at everyday speeds. They used a special medium and a spatial light modulator to slow light dramatically. This created a miniature slow-motion universe in their lab. Now, they could simulate relativistic effects without a spaceship. Everyday objects could mimic cosmic speed limits. By changing the speed limit of their tabletop universe, they unlocked a way to visualize Einstein's prediction. Slowing down light, not matter, was the breakthrough. It was a triumph of experimental ingenuity. The Vienna team's experiment blended optics, computers, and creativity. Instead of a real cube, they projected a light cube, shaped and moved precisely by computer. This light cube became their fast-moving object. They projected it onto a special screen that could control the speed at which the image formed. By programming the timing, they made the light cube move at a controlled speed across the screen. The light signals traveled slowly, creating a slow light medium. A high-speed camera filmed the light cube as it moved, capturing the time delay effects. The illusion of rotation became large enough to see in real time. When they ran the experiment, the results were stunning. The camera showed the cube appearing to rotate, just as predicted, straight edges curved, and the back face appeared at the front. they had finally filmed the Terrell-Penrose effect. A thought experiment became visible reality. The Vienna experiment was more than a physics triumph. It was a collaboration between science and art. Physicists brought the math and technical know-how, artists brought the power to visualize and communicate. Together they chose simple shapes like the cube to best demonstrate the effect. The result was not just scientific proof, but captivating visuals that anyone could appreciate. Art turned abstract data into a shared human experience. The animations show a glowing cube twisting in impossible ways, making the physics feel real. You don't need to know the math to be amazed. This partnership lets science escape the lab and enter the public imagination. Science and art together help us explore and describe our world. They make even the strangest ideas clear and beautiful. Why does filming this effect matter? Because it bridges theory and reality. For a century, relativity was proven indirectly, by eclipses or GPS corrections, but always abstractly. This experiment gives us a direct glimpse of relativity in action. Visualizing the Terrell-Penrose effect brings Einstein's universe to life. It replaces the old wrong mental image with a new, accurate, and fascinating one. It inspires curiosity and shows the power of creative problem solving. For 60 years this effect was just a prediction, now it's something we can see. Seeing is believing. Visualization makes complex ideas part of our shared understanding. This experiment opens a new window into the cosmos. It reminds us that the universe is full of wonders, waiting for us to find new ways to look. It makes the story of the cosmos personal and real. Einstein began with thought experiments, imagining riding a beam of light. His theories gave us a new vision of reality, but it always felt distant and abstract. The Terrell-Penrose visualization changes that, giving us new eyes to see relativity in action. We can now watch the impossible rotation of a cube and feel Einstein's physics directly. This journey, from a wild idea to a real experiment, is the story of science at its best. It shows that even the strangest concepts can be brought into the light. The next time you look at the night sky, remember, the universe is even stranger than we imagine. Thanks to science, we're learning to see it for ourselves.